All right, so in this video, we want to talk about the solution process. Now, the solution process, as the process of one thing dissolving to something else, right? It primarily depends on the strength of the attraction between solute and solvent particles relative to the strength of the attraction within the pure substances. Okay, and so let's first kind of talk about what type of substances will dissolve into one another. And usually, I'm sure you guys have heard this before, but the whole idea is like dissolves like. Okay, and what does that mean? All right, and we're talking about in the sense of polarity. Okay, now a polar substance will dissolve another polar substance. Okay, while non-polar substance will dissolve another non-polar substance. All right, and so really these are the type of molecules that will dissolve it to, right? And so polar, right? Um, so you may have two polar substances dissolving to one another, or you may have like ionic something ionic solute dissolving to a polar substance. So like in a good example of this, all right, when it comes to polar, let's think about alcoholic drinks, alcoholic beverages, right? The part that the kick, the alcohol itself, right? It's an alcohol called ethanol. So ethanol is C2H5OH. Okay, when you're looking into the structure of ethanol, all right, we see that ethanol is a polar molecule, all right, because it has this oxygen and this OH end, this alcohol. That's what they actually call it. This alcohol at the end of this organic structure. Okay. Now this causes that the structure overall is polar. Okay. Now most alcoholic drinks, or all alcoholic drinks, let me say that, also has water, right? And now when we're looking at the structure of water, right, we also see that water is a polar molecule. All right, so, and how are these two molecules attracted to one another? Well, it's through these intermolecular forces. We know oxygen is slightly negative, hydrogen is slightly positive. This hydrogen is slightly positive, this hydrogen is slightly negative. So it's this through this intermolecular force, that's how the alcohol and the water are attracted to one another. The attraction specifically in this case is hydrogen bonding. And we talked about this in a previous video. All right. So this is that strong attraction. All right. This is the whole idea of like dissolves like, polar molecules dissolving to one another. Okay. So that's an example of that. And then nonpolar is the same idea. So if you had two nonpolar molecules, like, so for example, you have like C8H18, could easily be mixed and dissolve into something like a C6H14. All right, so this is octane dissolving or interacting with hexane, and these two substances will dissolve into one another. All right, and so what we'll often find and see is that a polar molecule, all right, will not easily dissolve or have a strong interaction with nonpolar molecules. All right, and let's kind of talk about why. Like, why do we see this phenomenon, right? Like, for example, if you were to take a cup, right, and then you'll fill it with water, right, and then you put oil on top of it, you'll notice that they always stay separated, right? The water's on the bottom, the oil's on top. Especially like if you put the oil in first and then you put the water in afterwards, you notice that the water kind of just drops to the bottom and it kind of stick to itself. Now, obviously, the reason why water is in the bottom is because it's dense, but that's not the reason why they separate. Okay, now there is interactions between the water molecule and the oils, like right here at the border. All right, there is some type of attraction between the two. Now this attraction is due to London dispersion forces. Okay, so there is some small attraction between the water and the oil. But then what's going on really is that water within itself, all right? So if you look at water, you have the H2Os, all right? What we find is that water has such a stronger attraction for itself due to the hydrogen bonding, the strong polarity, right? What essentially will do is like it kind of pushes the oil out of the way, because all the oil basically here in this case, the only type of intermolecular force it has is London dispersion forces. And typically, if you're talking about substances within the same size, London dispersion forces are typically much weaker force than hydrogen bonding. And so, due to a strong affinity for itself, a strong attraction for itself, water would tend to kind of, click itself to the side and pushes the oil out of the way. And this is the reason why we see what we see. Okay. All right. So now the dissolving process is essentially a 3-step process. Okay. Anytime you're dissolving one substance to another, or let's make a quick example. If you're dissolving salt to water, okay, it's a 3-step process. Okay, the first step, in which it happens very, very quickly, but just to kind of get this point, the first step is the breaking of the bonds of the solvent. I'm sorry. Okay, and so what I mean by this, well, in this case, water, all right, is our solvent. And so here you have the water molecules, right? They're attracted to one another due to these strong bonds, all right? All right, so there is this attraction. Now, anytime you add a solute to this, you are now starting to break these bonds, okay? This process here is an endothermic process, all right? It takes energy. Why does it take energy? It always takes energy to break up bonds. All right, anytime you're breaking any type of bond, chemical bond, if you're breaking an intermolecular force, whatever the case may be, it's an endothermic process. It takes energy for this to happen. Okay, so the breaking of the bonds of the solvent. The second part to this is breaking of the bonds of the solute. All right, and so, like for example, if we're talking about salt, right, and we know that salt is specifically Na plus and Cl minus. All right, and so originally you have this NaCl. Now when you put it into water, you notice that what we notice is that it breaks to its respective ions, and so you have Na plus and then Cl minus. All right, and then you're just going to see that we're just going to have a bunch of Na plus and Cl minus. All right, and so you're breaking these ionic bonds. All right, we're breaking them so that it becomes its respective ions. All right, and so if you're breaking them, this process is also endothermic. All right, it takes energy to break any type of bonds. In this case, this is still true. Now, the third step to this, all right, and the third step of dissolving, and which is the last step, is the forming of the bonds between the solute and solvent. Okay, so what does this mean? All right. Now you have your sodium ions. What's going to happen is that you have the oxygen side of the water molecules attracted to the sodium ion. Why is this the case? Well, oxygen is slightly negative, right? It's partially negative. And so I'm going to kind of show this partial negative here. And we see that sodium is a positive charged ion. So there's this attraction between the two. All right. So that's the case on that one. Now, and then when we're looking at the chloride ion, we see that's exactly the case here, right? If we look at the chloride ion, we see that the hydrogen portion of the water molecule is attracted to the chloride ion. Okay. Now, because it's attracted to chloride ion, why is it attracted to the chloride ion? Let me answer that question. Hydrogen is slightly positive. Chlorine is negative. And so due to this, there's this attraction. Okay. When you're forming these bonds, anytime you form bonds, it's an exothermic process. All right. Energy is being released when this is taking place. All right. And so as you see, as I said, it's a kind of like a 3-step process where you're breaking the bonds of the solvent, you're breaking the bonds of the solute, and then there's a formation of these bonds between the solute and the solvent. All right. Now, when this takes place, all right, one or two things that you will notice, all right, is either that the dissolving process is overall endothermic or exothermic, meaning that overall, that when you was dissolving the substance into the water or into the solvent, that the overall process is endothermic. That means it takes in energy, or the overall process is exothermic. Now, how are you able to tell which one is endothermic, exothermic? Well, it really depends on the magnitude of each of these three parts, right? And so, what do I mean by this? If, the sum of the endothermic processes, like parts 1 and 2, all right, because the parts 1 and 2 is always endothermic, all right. If the sum of the endothermic process, the overall endothermic process, is higher than this exothermic process here at the very end, then the overall dissolving of that particular substance into the solvent will be endothermic. All right. And so as I said, I'm gonna say that again. All right. If the sum of the endothermic processes, all right, between breaking the bonds of the solvent and breaking the bonds of solute, if the magnitude of the amount of energy that's being absorbed during that process is much greater, or it's greater than the amount of energy that's being released by the formation of the bonds between the solute and the solvent, then overall this process is endothermic. Okay. But if, let's say, that the magnitude of the amount of energy that's being released during the exothermic portions, the formation of the solute and between the solute and the solvent, is greater than these two steps combined, then the overall reaction, overall process, physical process of dissolving that substance into whatever is it's an exothermic process. So overall, that means it's going to be releasing energy. All right. And so this is how a solution works.